All right, there is a temperature dependence to solubility. That's what we talked about a little bit with our idea of recrystallization on the last section. When we increase the temperature of a solvent, most solids will have a higher solubility in that solvent then. So that's when the delta H of solution is most likely endothermic, all right? And most solids dissolving in water have a delta H of solution that's close to zero. It's typically around maybe 2 kilojoules per mole or -2 kilojoules per mole. They're typically very, very close to zero for that delta H of solution. So for most solids, the solubility of the solid increases as we increase the temperature. The solubility curves that you see here with lots of beautiful colors can be used to predict whether a solution with a particular amount of solute is dissolved is saturated or unsaturated, right? So the line tells you saturated. If you're above the line, you're super saturated. If you're below the line, then you're unsaturated. These solubility charts you don't need to memorize. It's just, again, to be able to look and to navigate an X and Y plot. The temperature dependence for gases in water. Okay, let's think about gases. Why, when you open your soda, do you, if you don't finish it all, why do you put it in the fridge afterward? It's because you want it to stay bubbly, right? Gases generally have lower solubility in water than ionic or polar compounds because gases like to be by themselves, right? Usually gases with a high solubility are actually ones that react with water. For all gases, the solubility of the gas decreases as you increase the temperature. And that's because the delta H of solution is exothermic. You don't need to overcome any solute-solute attractions for gases because they don't have any, right? And so it is favorable to mix a gas with water. However, when we increase the temperature, we are actually making the solubility decrease. And the reason for that is because when we even think about gases locked in the liquid, that is not super like a gas, right? Gases like to be independent and like to move around. So the more kinetic energy you give them by increasing the temperature, the more likely they are able to escape into the gas phase. So solutions, even for gases in water, have that temperature dependence. They're just opposite of solids, okay? How can you make a solvent hold more solute? Well, you vary the temperature and or the pressure, okay? When you think about soda, if it's open to the atmosphere at 1 atm, you put it in the fridge to keep the carbonation there, to keep the carbon dioxide inside. If you think about a soda before you open it, right? Take a moment. If you have a soda with you, go get it, right? Go get it, bring it back, put pause maybe. It fizzes right when you first open it, right? When you go, right? That is because inside the can, there is a pressurized solution. It's usually around 4.4 atm of carbon dioxide of that extra head. That's why there's that extra head of air in the actual soda. One, it prevents your soda from like totally spilling on you if it was totally filled up to the top, but it's also there to pressurize and keep the carbonation inside the beverage, right? Don't shake your soda can before, because your shaking actually is making the agitation, giving that kinetic energy to the carbon dioxide in there, and it's making it making the vapor pressure increase. And so when you then, open the top, it all just flows right on out after you because the carbon dioxide's like, yeah, let's get out of here. So keep your soda in the fridge, don't shake it, and next time you open a can, be like, change of pressure, change of solubility. Awesome. There is a calculation that we are going to be able to do. It's called Henry's Law. Henry's Law is the ability for us to calculate the solubility of a gas and see how it is directly proportional to the partial pressure of the gas at a specific temperature. Here is the overall calculation. S, or solubility of the gas. I can spell for sure, is usually in molarity. All right. KH is called the Henry's Law constant. That is usually in molarity per ATM. And therefore, the partial pressure of the gas is in atmospheres, ATM. So there's our beautiful particulate diagram. Next time you go to a party, show this. That gets everybody super excited about chemistry in real life. So each gas has its own Henry's Law constant, its own KH at specific temperatures. Okay, so the KH for carbon dioxide at 25 degrees is 3.4 times 10 to the negative 2 molarity per ATM. We'll do many more calculations with Henry's Law in class, but let's continue and move on. Concentration, right? We're just brought up molarity. Is molarity the only thing that we need to know about solubility? No. Solutions have a variable composition. And so to describe the solution, we do need to describe the relative amounts. And what we have used before to describe concentration is molarity, right? Molarity is moles of the solute per liters of solution. This ratio can be either dilute or concentrated dependent on how many moles are in the given solution, right? A big molarity would be a concentrated solution. A very, very small number for molarity would be dilute. Those are qualitative terms just to be able to describe the state of the solution. But concentration itself is the amount of solute given over the amount of solution. Tons of different units, okay? So these are the units we're going to be holding in this section. Molarity, we know. Molality. Molality is used specifically with volume to mitigate volume dependence on temperature, okay? So volume for a liquid is relatively definitive, right? It's 1 milliliter of water is 1 milliliter of water, but as you start to increase the temperature of that specific water solution, volume does expand a little bit. So some chemistries use molality instead so that there is no temperature dependence, okay? Mole fraction, it's the amount of moles of solute per total mole. We've kind of seen this one when we did gas laws, right? We did gas laws and we did moles divided by total moles. So that's there. Mole percentage, slap on 100%, and you can see a mole percentage. Parts by mass. We did this a lot when we kind of did mass percent, right? You can see the next one under there is percent by mass, where we took mass of the solute divided by mass of the solution and multiplied by 100%. We were doing mass of the atom divided by mass of the molecule to do mass percents previously. Same concept is here for a solution. Parts per million by mass and parts per billion by mass is using a multiplication factor of 10 to the 6 or 10 to the 9. And what you get out of that is a unit of ppm or ppb. These two are really heavily utilized in industry, specifically in water treatment plants. I was a water chemist for the Southern California Edison Electric Company for a really long time, 4 years right after school. And so when we use these was for drinking water standards, right? So relating to environmental, like EPA, in the state we have ELAP standards. So if you live in a city that either mails you your water report every quarter, or you can look at your water report, look at it. You'll see ppm and ppb are used for things like fluoride or metals, cations. If you have heavy water, if you've ever heard heavy water, that's not great for pipes because calcium ions and magnesium ions are in the water, naturally occurring, totally fine for us. We like those because then our body can actually absorb the water better. However, it can cause scaling on your pipes, and so your pipes can corrode a little bit or get some scale on them. Things like that. So these are for very, very small solute amounts, very dilute solutions. Use ppm or ppb. I do expect you to be able to utilize all of these, okay? We will talk first a lot about molarity because it's familiar to us. We definitely want to know molality though as well. Molality we'll see at the end of this chapter being extremely useful. Anything that has a volume is temperature dependent, all right? Temperature dependent is not great because as we increase temperature, then the concentration is technically changing already. The actual description of a solution is changing. And so our non-temperature dependent concentration units are going to be the ones that only deal with moles or mass. Those two things will never change. Volume is temperature dependent though. All right, so preparing a solution, right? If we're thinking about doing that in the lab or at home even, need to know the amount of the solution and the concentration of the solution. So you've seen all of these types of calculations before. You either need to calculate the mass of the solute needed, you are given the amount of the solute needed, and you need to find the concentration. There's a couple of different setups, but overall, if you're in the lab, you would want to say you would dissolve the grams in enough solvent, or grams of solute, excuse me, in enough solvent to equal that total amount of solution, right? We've done these types of questions before where we weigh out a specific amount, we would pour it in to a flask and then dissolve enough water. This is a volumetric flask. Volumetric flasks are great for preparing solutions because there's one mark that is standardized to that specific 1 liter. And it's standardized so well that as long as you reach that meniscus to that mark, you know you've added enough volume of your water to reach a 1 liter, perfect 1 liter solution volume, okay? Molarity, these couple next slides just again describe the unit. We're gonna practice with calculating that unit when we get into class. Molarity, super, super important. Molality will be even more important. Notice the difference here. Little m for molality versus the big M, capital M for molarity. Be very specific when you're talking molarity, molality. They sound the same, they look the same. Notice the denominator now is kilograms of solvent. It's specifically relating the solute to the solvent, not the solution, and it's not using volumes. So it's not temperature dependent anymore. That's why molality is like super special. Parts of the solution, these are, we can do mass per mass, mass per volume, volume per volume, all of these different things. We won't do them too much. Specifically because we are going to be dealing with colligative properties in just a little bit, and those use molality. But again, parts per million, specifically 10 to the 6th as that factor, all right? And parts per billion, 10 to the 9, right? Billion. Excellent. So mole fraction we've seen before for understanding gases. We can do them as well for solutions, all right? Mole fraction is moles of one substance over the total moles. Mole percentage, just multiply it by 100. We will be converting between concentration units. The best thing to do if you are given a concentration unit is to write it as that ratio. Don't just say 1.0 molar. Right? Convert it. 1.0 moles of solute, again, be specific, per 1 liter solution. Write it as that fraction because then we will be able to use conversion factors to take this wherever we need to go, whether we change the numerator or change the denominator, okay? We may even need to separate the denominator. We're going to assume that we have 1 liter of solution, and therefore we have 1 mole of solute. All right, so we might even need to separate these to convert them and separate the solution to the solution part. All right, the solute part and the solution part. And then we can convert them separately, which is what 3 and 4 are describing. And then we'll define a new set of units. If we wanted to convert to molality, say, well, we can use that 1 mole of the solute, but we do need to find the kilograms of just solvent. So we may need to do some fancy footwork separating these two to convert this to kilograms of solvent somehow, right? Using density, subtracting things, all sorts of lovely stuff.